This conference will now be recorded.
Okay, Al, whenever you're ready. Hey, so this is the first of a sequence we're going to do of expanded versions of hip chips talks. Tawfiq, if you've got any recommendations, DJ gave me a few. You attended hip chips. If you've got any recommendations of people we should invite, please let me know. So the idea is to take those 10-minute, 15-minute talks and maybe expand them a bit. That's about it. Sorry, Alan, looks like we have a light turnout today, which seems to be an issue all summer. So
no worries.
But we appreciate your time.
We'll have the recording as well, so that'll be fine.
Sorry,
Okay,
Buffy, I missed something. You want invites for what, the workshop or the regular
No.
meeting?
If you know of any other talks at Hip Chips which we should expand, DJ gave me 3. So if you've got any talks that you attended at Hip Chips that you want to expand a bit,
Oh, I see. Sure.
because this
Yeah,
is Alan's talk that we're expanding to 30-40 minutes, and so maybe there are other interesting things at Hip Chips where people got 10-15 minutes, right?
yes.
Yeah. So if we want to expand those, that's the plan for the next few weeks.
Sure.
Well, I guess this was part of my great fight argument as well. So we shouldn't now new recall if that's still going ahead or not.
We'll see if we can carry it forward, but for now, like it's more like the Hip Chips talk, and then we'll expand it.
Yeah. Okay. Shall I kick off, or you want to wait anymore?
No, please get started. Thank you.
Okay. All right. Well, hi everyone. First, can I ask you to allow yourselves to think outside the package when listening to this chiplet presentation? Excuse the pun. So this is redefining computing architecture boundaries with off-package chiplets. And this is very much an energy-centric computing perspective. Oh, hang on a minute. Sorry, let me change. Okay, so what are the drivers of computing architecture today? Really, there are 3 main ones as far as I can see. First of all is power and sustainability. Energy efficiency is ever increasingly important, and we're trying to rapidly drive performance. So it's a struggle to just stand still in terms of energy consumption as performance goes up, and we're also trying to get energy recovery. Cost is a huge thing as well, and open architectures really do allow us to drive down costs, which is what we're all here for in terms of the OCP side, getting the open architecture and getting the best architectures out there. And finally, domain-specific architecture composability is a huge topic in terms of allowing you to build the most efficient computing architecture for a given application. Being able to physically compose the components to do that makes a great difference, and I'm going to focus a little bit more on that one. So I've got 4 areas. The first one is not composable, it's the fixed architecture. The classic example is the mobile phone chip, where you've got lots of heterogeneous processors crammed into the one chip. Very inflexible in that sense, but targeting a huge market in a very power efficient need because of the handheld mobile phone. So that's the first, but at the opposite end of the scale, across our industry, we've had the classic traditional server architecture, which I've coined the pluggable physical composability. Everything's pluggable: the memory, the processors, the network cards, PCI cards, and accelerated PCI cards, and storage. Everything's pluggable. And then I've coined the term the chiplet implementation is really hard physical composability. And what I mean by that is really we've sucked the entire server into the package, if you look at it. And it's composable, but it's composable at the manufacturing time and at quite an expensive cost of the packaging time. So it's not an IT engineer can quickly swap these things around. So I've called that hard physical composability. And then finally, we have dynamic software composability, where we're actually disaggregating all of the components, computing architecture components, into their own drawers in a rack, and then reconnecting them with software, giving you this dynamic software composability. So let's take a closer look at the chiplet area. So what is the motivation for chiplets? Well, first of all we ever do as an industry, sorry to say this, but is do compute and data. And most of the architectural efforts over the last few decades are all about circumventing the von Neumann bottleneck. And so it's all about improving the data to compute movement efficiency. And we've had Moore's law for decades, really just doing that for us without us really realizing, shrinking everything. We got to such a point that the processing was fantastic, and then we had so we started pulling the memory on board and with cache-in to again circumvent this bottleneck. Then we moved on to heterogeneous processors, where we reconfigured the processing in the memory for certain application efficiency, so that you basically could process on silicon more efficiently. And now we're seeing this moving everything closer together. All of these server components are sucked into the package for more efficient communication, chiplets in the package in 2D, 2.5D, and 3D. So, but what about off-package I/O? So system size rarely shrinks when we suck more into our package. And you guys are doing a fantastic job, and we're in the 0.5 picojoule per bit area. But off package, we suddenly get a 20x increase in energy requirement to move that data off the package, and we do need to still move it. But we've got this promise of co-packaged optics is going to save us all from this problem, right? Ultimately, what we want to do is we want the highest system performance at the lowest energy and cost. So let's take a closer look at the data. So this is a table.
Are you sharing any slides, Alan? I'm sorry, I don't see your screen.
I do see.
I think it is Reza. It might be a local problem.
Oh, okay. Sorry, guys.
No worries.
So we've got these we've got typical Fire I/O standards shown here. If we look above the green line, this is typically what we see today in a standard server, and we're in the 10 picojoule per bit region. And below the green line, we can see what chiplets is bringing us. It's bringing the I/O power into the 0.5 picojoule per bit or even less region. In the green lines, you can see that the promise of silicon photonics, you can see why we're excited about it, is this is hundreds of meters of distance for around about a picojoule per bit. And one other one worth considering is that we have considered in ODSA is the OIF very short reach, which can give us 160 millimeters at around about 1.5 picojoules per bit. So we want to look at the potential of off-package chiplets. An off-package chiplet with this particular PHY is what I'm going to utilize in this presentation.
Sorry, Alan, can you go back to the slide? Sorry, I have one question. Why VSR is going to be 1.5 picojoule per bit? It's even more than XSR, and XSR also is more than that.
I've got that from the specs. Also, analog X's OAF VSR from the tables you created. That's where I got the number from. And I think in the specs, the OAF is set around 1. So yeah, that's the number I've got. If it's wrong, then let me know.
Sure, definitely is way more than that. I think analog X wasn't VSR, but we can talk about offline. But if you're calculating 1.5, we need to talk about it.
Okay, so well, the idea here is a relatively short reach is in trying to gather energy, because all classic I/O is trying to drive at least a meter across PCBs inside the server, or several meters over cable, right? So we're always in the 7+ picojoules per bit for other approaches. By the way, I did do the analysis in OCP HPC. with IBM's support, we did the analysis of a channel, of a short channel, and using bringing the energy down, and with a loss of around about 5 to 10 dB, and we were certainly in that region. So I don't know how far out we are. Maybe it's 2. I typically use 1 to 2, so I use the 1.5 for this. So let's take a look at traditional local memory. Let's say a traditional server where we've got local memory, and we've got an RDMA is the way to get it memory from another server. If we look at that, and we look at the on and off package configurations. So I split the memory capacity, I split the chart into different memory capacities, as you can see there. And also I'm showing bandwidths of that memory channel and the actual I/O power consumption that we see. So if we look at this traditional memory, we're seeing the likes of 3 terabytes of DDR5 on AMD's latest EPYC devices. And if you do the power analysis, that's around about 50 watts for that given bandwidth that you can achieve. And that goes up to the 3 terabytes. And when you go beyond the 3 terabytes with RDMA, you can see we get quite a significant jump up to around about the 400 watt region. And this is with passive copper interconnects for your network connection in just one hop. If we look at the trending as to where we're going with CXL shared memory, the common view is that we're sucking the memory on package, the HBM, with this, and then we're going to deeper memory into the CXL memory pools. Now we can see that the first 80 gigabytes, the HBM memory, is fantastic. We've actually halved the power consumption, and we've 5 times the bandwidth. So we've got a 10x improvement. So we can see why HBM has been so successful when you need this sheer bandwidth and without burning more power. So that's great. But when you want the 3 terabytes of local memory, you now have to reach into the memory pool. And we can see that there's a 17 times increase in power to reach that memory pool versus the local traditional memory for only 3.5 times the bandwidth. So energy consumption is going in the wrong direction with this new architectural shift that we are currently on. But let's look at the co-packaged optics is going to save us, right? So let's look at a co-packaged optics version. This is a UCIe example here. We can see that actually the power increase is still 9 times for 3.5 times the bandwidth. So we are still taking energy in the wrong direction. So what if we make, what if we try to get some local memory and actually make it CXL shareable using this very short reach interconnect? So we have a shared memory buffer where you have a local connection to your CPU, and you also have a second port to share, to be shareable across the CXL fabric. Well, when we look at this, up to 8 terabytes of local memory can be configured, and that's a quarter of the power consumption of the CXL electrical implementation. And this electrical implementation is even half the power of the of the co-packaged optics implementation. And then when we go beyond 16 terabytes, beyond the 8 terabytes, so we're reaching into the memory pool of somebody else's local memory, we're still 3/4 of the power of the CXL electrical pure CXL electrical implementation. If we actually optically enable these local pools that can be shareable via CXL, we are the overall power winner. And so if we look at this, if we bring all this together and we actually normalize it to a watts per terabyte per second memory sharing comparison, we can see that the off-package shared memory chiplet approach is the overall winner. And we can also see the green bars are showing this. We can also see in the silicon photonics, it is still the overall winner. So switching gears a little bit, this is just a quick observation.
Alan, sorry. In the previous slide, why, if it's off package, why is it a chiplet?
Well, okay, so I call it off package chiplets because you can't go very far. It's still a so yeah, maybe my naming is bad, Bappy, but at the moment, if you look at it today, we are starting to sprinkle retimers everywhere, even getting to an optical module, right? So we talk about co-packaged optics, but we could do near packaged optics. It's all about, can we reduce the energy of the I/O? If you look at the I/O energy, it's tremendous. And silicon photonics is expensive, and it's how quickly are we going to get there efficiently? And even if we do, this is a more power efficient way of doing it. So this is going more memory centric is the bottom line here. But yeah, I call it off package chiplets because it's taking the chiplet idea of saving energy and bringing things closer together and saying, we can do this outside of the package.
But
Okay?
if it's not going to be shared, if it's not going to be shared with another, oh, I see, in your thing, it's going to be shared across multiple entities, basically. That off package. Of course. Okay.
Yes, of course.
That's a part.
Yeah, so you've got the local, you've only got 1.5 picojoules per bit for all I/O off the processor. So you take up burden off the processor for all of the electrical I/O that come off package, because they wouldn't typically be 7 picojoules per bit. So you've saved energy there, and as the bandwidths go up, that's huge. And then the second port, you can share either electrically or you can put the silicon photonics into the tiny little buffer and have near packaged optics. And by the way, suddenly you can then go to Foxconn with 2% margins and build your boards and not have to spend millions of dollars on redoing a package. And you can also make it pluggable, so an IT engineer can actually reconfigure these things. Whereas at the moment, an IT engineer cannot. It's the manufacturing people can. So it's no good from a standardization perspective. Is that right? Is that okay?
Yes,
okay,
thank you.
So just looking
yes, it is. Thank you.
Yeah. Okay. So just looking at HBM, this is now I know this is just a quick observation. Basically, a bunch of wires or the UCIe standard could actually be used as the HBM interface and actually keep up with the HBM demands for bandwidth in an organic substrate. I've shown in the picture there, I mean, basically, the HBMs are a physical size of the memory chiplet itself, and there's plenty of beachfront to actually use one of these other standards. And so that might be a way to get to a lower cost organic HBM implementation. If we put all this together, then I've got this proposed chiplet industry standardization where we utilized a bunch of wires and the OIF very short reach PHYs for on and off package chiplet I/O respectively. We leverage cost-effective organic packaging, and we end up with this unified off-package I/O for all processors that will democratize compute. So you'll be able to swap in and out different processors because everyone just uses the same I/O. And this effectively will then be accessible to tier 2 and tier 3 players. And let's face it, there's no point in making an industry standard if only the billionaires club can use it. They do their own custom stuff. So with this proposed chiplet industry standardization, I've just shown a traditional motherboard implementation, and you can see the chipletized packaged in the organic substrate, and you can see the off-package chiplets as I've coined it. So yeah, happy, fair point. Is that a good word to call it? But the off-package chiplets are simply I/O translators. They're bringing a standardized I/O for the processor, just like we have standardized I/O for memory, and they make it specific to my needs of NVLink or I want to attach some memory, or I want to do near packaged optics, and so for differing I/O use cases. But as well, in OCP HPC, we've got some more innovative, novel pluggable chiplet 3D, where we actually think about 3D at the system level. It's all great to do 3D at the package level, or 2.5D, etc. But what about the system level? So let's shrink the server into a little module where this 1.5 picojoules can actually, we've got the data and the compute close to each other. And so that we've got the opportunity there where we're saving energy. So in summary, today's disaggregation models are driving energy efficiency in the wrong direction. And if we supported off-package chiplets at I/O standards, this would really allow us to have a graceful increase in power, as I've shown, but also latency when moving the data. We'd have a more flexible and composable computing architecture. And really the potential for the I/O unification across all heterogeneous processors. So that would make it much easier for users to swap in and out different heterogeneous processors at the system level. And that will ultimately give us a lower cost, sustainable, and competitive ecosystem, which I don't believe is happening otherwise. It's just too inaccessible. It's like I say, it's a billionaires club. It's a tier 1 billionaires club, this benefiting from this. So thanks very much. That's it. Happy to take any questions.
So I want to go back to the slide 3 slides ago. The thing that's puzzling me, that I'm kind of confused about, is
which slide is it there?
No, that one. The 2.2 above that. Yeah, actually, the jump from 11 to 12. So
The jump from 11.
Is, like, we've got all these figures of merit that Shahab is, I don't know if he's online or is, Shahab is driving, right? So
I'm online.
So the part that confuses me is, why will the relative relationship between these different interconnects change when you go to something like memory? When you sort of go up level and measure and include memory bandwidth, wouldn't it be all this? I don't know how to form the question. Maybe somebody can form the question better than I can. What I'm trying to say is, like, if interconnect A is better than interconnect B at our low level metrics, why would the relative relationship change once you sort of go to a new metric like bandwidth, bandwidth in terabytes per second?
Well, it's all about the energy, right? So every hop is consuming energy, and so you have to analyze the entire energy across the entire system. And so what CXL is doing, what we're proposing, first of all, parallel DDR on your processor consumes huge amounts of beachfront, and the memory controllers are pretty huge as well. And so you don't end up with much beachfront left for your CXL IO or your HBM. So either the local memory disappears, or we serialize it, which is one potential thing, which is what we're saying with the likes of OMI. Or we go purely to local memory only being HBM, which is the example I've shown. Basically, from what I've heard from Intel and everybody, is we're going to suck memory on package, and 80 gigabytes is enough memory for the local requirements. And then when we need more memory, we reach into the memory pool.
So
yeah, today's servers. Yeah.
One point, sorry for interruption. When you say 80 gigabit of memory is enough, what type of memory you are talking about? High bandwidth memory?
80 gigabyte HBM is so basically I've used NVIDIA's A100 example that uses 80 gigabyte.
And you think the limit is more than 80 is not useful?
No, I think it's probably going to go to about 250-ish before the wheels fall off.
Great.
Wait, This sound
So you could replace that with 250 if you like.
You finish, Alan. Sorry, apologies.
No. I got my
No,
point. Basically, those numbers are.
I mean, look, sorry, go on.
Basically, the memory that we are quoting over here is a HBM. We are talking about the HBM band. That's one thing that I wanted.
For the 80 gigabytes. Yeah, for the 80 gigabytes. You can see how power efficient that is, and for a tremendous bandwidth increase. That's great. That's why HBM's used. But so the argument is, when you listen to the argument, is the industry is saying we only need 2 to 4 gigabytes per core, and therefore 80 gigabytes is enough. That's 40 cores. So like we're already hitting 200 cores with some of these processors. And
wait.
I think
So yeah. I think I'm losing the plot in the transition. Not losing the plot as in a negative sense. At least I'm not able to follow the logic thread going from slides 9 all the way down to the final conclusions. Like, if I understand this slide correctly, you're saying, hey, if I had an off-packet chiplet, right? So which isn't too far away, and here when you compare the three options, if you go to the next slide, or the one before slide 11, if you go to slide 11, you're comparing, the options are basically if each CPU has its own memory versus one shared memory pool. That's the basic comparison.
Each memory has a slice of the CXL shared memory pool local to it, rather than having to reach across the network to get it. So the key area to look at is the 3 terabyte and the 8 terabyte column, because we can connect 8 terabytes of CXL with 256 lanes to a CPU if you have no parallel memory. You could probably get to 512 lanes before you really hit package issues. So I've got 30. This is based on 32 channels of CXL being locally of memory being locally attached to the CPU and shareable over a CXL fabric.
Okay, so basically the memory the little 8 terabyte memory buffer is local to that CPU, and then this other one, between the CXL shared memory buffer and the CXL switch is this optics cable, basically.
Yeah, which is assuming that co-packaged optics is successful in the switch, and which is what I hear broadly. People are going to say the switch is going to go adopt co-packaged optics first. And you can also, because this shared memory buffer is such a tiny little chip, you can actually probably integrate the silicon photonics into the 2-ported buffer with the memory much more easily than doing co-packaged optics with a damn great big 800-watt GPU. So the idea is,
go ahead, Alan, please. Sorry.
Yeah, so essentially that this buffer, if you look here, this buffer, this CXL shared memory buffer, is got this local connection to the processor. They can see this memory, this 32 channels of DDR5 memory. It can see, and it can use, just like a traditional server uses it through a parallel DDR bus, but this is serial. And at the same time, it's a dual ported buffer. So you've got here in this case a silicon photonics port talking CXL to share across a CXL fabric. So on the processor on the right, when the processor on the right wants to access the processor on the left's memory, it sees it as a CXL pool. It's some distance, so it is borrowing it, so it has to go through the switch. But it's also got its own local 8 terabytes that it can share with everybody else. And so what we've got is we're looking, this is a truly data-centric view of the world. And now everyone's going to say, when the speeds get really high, you know, basically you're limited to about 5 terabytes per second when you do traditional off package. whereas HBM, for instance, is probably going to get to 20 terabytes per second on the package. But if you think about that, what you're really sharing is the data. You know, it would almost be better to just have the high bandwidth accessible to the silicon photonics in the memory itself, in the little memory shared memory part. Anyway, that's I'm going off on a tangent there, but to focus back on this is basically we are keeping the traditional servers view that AMD today build their EPYC can support 3 terabytes of local memory at 50 watts of I/O power. To get so if you look at the chart, Bappy, you can see that it's 50 watts to get to 3 terabytes on their traditional server. If you want to get to 3 terabytes on the purely CXL implementation with no local memory except for HBM, it jumps to 850 watts to access the same amount of memory, the 3 terabytes. Now, people say, I only need 2 gigabytes per core, HBM is fine. But if HBM is fine, that's beautiful for the averages. Why do people configure servers with 3 terabytes? Because they're doing transactional in-memory databases. AI and ML needs terabytes of memory at HBM type speeds. And so we are going to see a pull, and this is only 2 terabytes per second, by the way. This is not as high as the HBM. And we're hitting 850 watts. Now, even with the silicon photonics, we're still hitting 450 watts. And so this is the problem. When you start drawing these architectural diagrams from an energy-centric computing perspective, you get a whole different view of computing. And if there's one thing that our industry is focusing on right now, is power is a problem, not only for the power density on these damn modules, but because of sustainability and the projections that computing is going to kill us in terms of ever increasing percentage of the world's energy. And yet we're just blazingly just marching along, putting CXL, just saying, let's pop a shared memory pool at the top of the rack and access it through a bunch of switches, happy days. Well, and suddenly we're burning 17 times more power for 3.5 times more bandwidth. It's just untenable, untenable. And so, and what I'm doing is, you guys are all so focused inside the package because you're silicon guys, right? You're silicon in the package. You don't give the systems engineer a single second to actually say, think about everybody in the chain. You might have the perfect world for you, but what about the guy next door? And the trouble is, we're driven by the silicon. We're driven by the incumbent silicon. So we're marched along, and systems engineers are at the bottom of the food chain. We've got to build a system out of what you guys give us in components. And we're trying to create a standards body here. A standards body mean that the ecosystem of system players can actually buy individual components and put them together. But there's no bloody way that a tier 3 player is going to build his own chipletized package because he wants to put a different heterogeneous processor in there to what somebody else supplies. So if we're going to do industry standards, this is the way we've got to enable this, and this is a good approach to it. And by the way, silicon photonics has got a damn long way to go. It's still sort of like a decade away, really, to be there fully established. And so doing it in a timely shared memory buffer rather than doing full-blown co-packaged everywhere. I mean, are we going to have silicon photonics in a CXL memory device next week, next year? Or is this, or is the individual media device is going to go, if you could magic the entire world is optically connected outside the package overnight, then okay, I throw my towel. Let's do it. Let's get it. But there's no flipping way that we're not going to. A fully optically enabled out of package architecture is not going to happen for about a decade, and I reckon that is the ultimate destination. But we've got to work a way to get there steadily, logically. And I agree that maybe silicon co-packaged at the switch level is the first nut to crack, and then co-packaged at the processor levels maybe, and then co-packaged at the media and co-packaged at every damn component. But
Wait.
that is a
So
massive change.
so I'm trying to get the, I guess in my head I'm trying to go from slide 12 to 13 in your deck.
Okay.
So you got slide 12,
So
which kind of
12.
says here is my, or slide 12 to 14, excuse me. So 12 to 14 is what I'm trying to figure out. How does slide 12 relate to 14? And
Right. So slide 12 is just a summary of all those previous slides.
right.
So it's showing the blue one is a local traditional server. You can see that up to 3 terabytes is really low, well, not really low power, but it's low power. And then when you do RDMA, it jumps up pretty badly in terms of watts per terabyte per second. The CXL only solution, or the CXL shared memory pool in HBM, you can see that at 3 terabytes, it kills you at 3 terabytes compared to a traditional server. And if with the local shareable, CXL shareable memory, the local one, you come back to almost the same as a traditional local memory. And there are other things you can do to improve that, which I won't go into here. But every single graph, bar chart for every single capacity increase, it's still the winner. It's still the green bar is still the lowest bar in terms of a watts per terabyte per second. And when you do the silicon photonics version as well, it's the same answer. So the silicon photonics argument,
you need a local cache, network cache.
I'm not even touching on the cache side of it. I'm just saying this is local memory that's directly accessible to the processor, just like a traditional server.
And then so from there to 14.
So the left graph is based on local, local memory, essentially, right? And the right side is with the remote.
No, the left is a copper interconnect, and the right is a silicon photonic interconnect.
In the chart, the blue one is local memory, and
oh yes, sorry, Michael. Yes, yeah, the blue one is a traditional server with 3 terabytes of local DDR, what we all know and love. And the red is local memory, is just the 80 gigabytes of HBM. So if we go to 80 gigabytes, you can see that HBM is fantastic. Look at the drop compared to a traditional server, fantastic. But when we want to access that 3 terabytes that we configure local memory on the traditional, by heck, CXL screws us big time. CXL shared memory, right? And but if we actually put that CXL shareable memory as a 2-ported local memory buffer, so we share it locally with one processor, and we lend it out over the CXL fabric, all we're doing is rearranging the CXL shared memory pool. Instead of having one pool in the middle of the world, we're putting little buckets of the same pool local to all the main processors. That's all we're doing.
So when suddenly you say the XL memory pool in the slide 11, right? Can you go to slide 11?
Yeah. So all of these are shared. Both the red and the green are shareable over CXL. The CXL is still there, center of attention. It's just how you slice up that shareable memory. They're both shareable.
So basically, local is to the left of the CPU in your picture. Local CXL is to the right of the CPU in your picture. If you take the CPU on the left, it's behind and in front of, right? Roughly in your pictures.
Which one are you looking at, Bappy?
So if I look at the blue one, corresponds to in slide 11, it corresponds to the memory to the behind the CPU, which is only a connection to the CPU, nothing else.
Yeah, the very first slide. The very first slide. This one. So basically the first bar is, sorry, which color? The blue bar is this traditional server. So you've got 3 terabytes of DDR5 attached to 12 channels. This is basically 12 channels of DDR5, 3 terabytes, 256 gigabytes of stick connected to these. So it's epic. It's the latest epic.
You're overloading the term local to mean 2 locals. One to the one in this picture, the mustard colored thing, and later memory that gets attached to the right of the CPU.
Yeah, so from the left-hand processor's perspective, the left-hand memory is local.
Yeah.
From the right-hand processor's perspective, the right-hand memory is local.
But if you go
It's two
now to
servers.
the next, if you go to the next or third picture, the slide 11 or something.
Oh, I have a question on this slide. You know, in this page, between 3 terabyte and 8 terabyte, right? There's the power consumption is, you know, increased a lot, like 8 terabyte case, 373.
Right.
So how,
Yes.
I mean, how you got this, you know, number in this picture?
Well, so all the data is there, Michael. So if you look, you've got the 7 picojoule per bit channels. You've then got a NIC card to get it into fabric land. This is a traditional server, right? RDMA over Ethernet. So then you've got 7 picojoule per bit on driving out your NIC, and you've got a copper cable. So there's a passive copper. So there's no active. So it's an optimistic configuration. And then we've got the switch itself, with their 7 picojoules per bit per port. And then we go across to the NIC on the other side, and then over the PCI bus to the CPU. You add all those picojoules per bit. I think this comes to 49.7, 1, 2, 3, 4, 5, 6, 7, 8. 5, 8 is 40, 56 picojoules per bit or something for this channel, plus the 10 picojoules per bit for the memory, and plus some picojoules per bit to move it across the CPU, which is a big piece of silicon, which I don't have a number. That's why it's 373 plus. So you add all those together, and then you multiply it by the bandwidth of 0.6 terabytes per second, and that gives you the power. And that's where the 373 comes from. So everything is in. I've even got additional charts I can show you where I did the math. So you
8 terabyte and 16 terabyte is almost the same.
Sorry?
Why 8 terabyte and 16 terabyte power is the same?
Well, effectively, to get to 8 or 16 terabytes, you've just got a switch with maybe multiple ports on it, right? So I've only shown 2 servers, but there'll be like maybe 8 servers or 16 servers off this switch, yeah?
So the
You can get
fabric to memory causing a whole lot of power. It looks like it in this picture, right? When you look at the
exactly, it's the fabric.
Yeah.
Exactly, Michael. Exactly, and that's my point. Is because you're moving further, you're moving outside, up and down a rack. These all really exist. This is a real server configuration. But the thing is, guys, no, we've never ever. We never look at the energy. Our industry has never drawn a diagram like this. And I'm trying to say we need to draw a diagram like this, because what we're realizing is if the bandwidths go through the roof, we're saying, well, we can get the bandwidths there, can't we, guys? This is great. We can even keep the energy relatively low. You know, it's been 7 picojoules per bit for a PCI link ever since the world began, sort of thing. But now, because the bandwidths are going up, in my presentation at Flash Memory Summit next week, I'm showing another graph that just shows as the bandwidth goes up for 7 picojoules per bit, we're at 600 watts for 5 terabytes per second, just for that I/O. And so when we start drawing it with an energy in the middle of our design, we start to realize how we can optimize the architecture for energy, which is the sole driver of the computing industry right now, is power consumption. We want performance, but at a realistic power consumption for many reasons.
Right. Yeah.
So
I always think, you know, size of a fabric is a matter. So I mean, keeping huge, you know, fabric to deal with the, you know, huge capacity sounds good, but in terms of energy, you know, may not be good actually. So.
right, and by the way, this is the most optimistic link you can build with a Ethernet switch. So, you know, you put 2 switches in, it just gets worse.
Right. Okay.
So the chart, the table builds up, and if you want to look at the real numbers, you can see the 3 terabytes, which is the sweet spot of the traditional server, right? Which is efficient, it's 50 watts, but it's only 0.6 terabytes per second. If you go to 2 terabytes per second, a CXL implementation is 850. A silicon photonic CXL is 450. My proposed local memory approach, shared memory approach with an energy efficient I/O, so it's really close to the processor, is 200 watts.
Yeah, so
And so
it would be helpful if you had a different word for the second local. Calling both local is very confusing. I'm not
what do
complaining.
you
I'm
mean by
saying
the second?
So locally, is actually, there's a CPU based on CPU. You can have a DDR, memory that is local, but you can have, CXL based extended memory that is attached to that CPU, which is a host that also, it can be local. That's
yeah. So I think you're using the word local to refer to
local
both the
to a
memory
host.
attached to the shared memory buffer and to the memory attached directly to the CPU, correct?
Yeah. Well, if you look at this, I think it's worth paying attention to the diagrams. I didn't dwell on the diagrams, but you can see that basically this is saying 32 memory channels, and you can see they're 1.5 picojoules. They're close to that CPU, and the same on the other side, right? So
Right. I'm just saying using the word local for both is very confusing. That's all. So the concept is
well, it is the same. Effectively, it's the same as this. It's exactly
yeah.
the same configuration, except for
I'm not
right.
complaining about the configuration. I'm just saying just the word local for both is like puts you, but at least when you're seeing this
Well,
concept.
I guess it's the same. This is memory is local to this CPU, and this memory is sorry, this memory is local to this CPU. It's the same. I mean, and obviously the HBM is local memory as well. And what we mean by local is 50 nanoseconds of latency access. That's a traditional near memory, or you could call it near memory or local memory.
Okay, Alan,
Right.
in this picture, talk about 16 terabyte plus that one, right? How we can map over here?
So there's 16 terabytes on this diagram, you mean?
Yeah, in this diagram, the last column, that's 16 terabyte case.
Right. So if you look, if you look at this, each DIMM is 8 terabytes, and there's 30. That's right. This is 38 terabytes, made up of 32 CXL, Samsung CXL. These might be 256 gig. I can't remember. You have to do the math rather than 512. But this is 32 CXL memories being attached here.
Okay.
Okay.
So you got 8
32 channels of it's 32 channels of local DDR. So I ought to repeat this 32 times. It's like 32 DIMMs. It's like the traditional server is 12 DDR5 DIMMs, and this is 32 effectively 256 gigabyte DIMMs in this particular one connected into this buffer. It can be CXL, or in this case we would be OMI, and my proposal is that this is OMI, but I didn't touch on this because I was only talking about the power, so I didn't mention OMI.
So okay, you're saying 32 of the 256 gigabyte, that means 8 terabyte. I mean, up to 8 terabyte I understood, but in terms of 16 terabyte with this picture,
yes,
you're
right. So 16 terabytes
for expansion.
Yeah, no. So 16 terabytes, you've got to reach across the CXL pool into somebody else's memory to get to 16 terabytes. So then,
I see.
So for 16 terabytes, let's say this left-hand processor wants to access this right-hand processor's local memory via CXL. Yeah. So now you do the addition here.
So you are assuming this is CXL memory pool. CXL, those 32 CXL 8-lane stuff,
Yes.
that memory pool as a independent pool, memory pool for any CPU.
Yeah, so the left-hand memory is a CXL shareable with the right-hand processor, and the right-hand's local memory is CXL shareable with the left-hand processor.
I see. Okay, I got
and
the picture.
So when you want to get to 16 terabytes, you've only got 8 terabytes of local memory, so you have to reach into the CXL memory pool. So when so this number here that you see here, the power number 656 in this particular example here, is if this processor is accessing the right-hand processor's memory, you've got 1.5 picojoules per bit times 2, then you've got 7 picojoules per bit. Copper cable, CXL switch 7, copper cable 7 to the switch, and then 5 plus 5 to the memory itself. Add all that together, and that gives you the 656 watts.
But what's
compared to the
connectivity CPU and CXL shared memory 1.5 picojoule per bit?
You can, because CXL by definition is a fabric, right? So you've got to reach across.
I mean, what kind of PHY we're going to use for that?
The PCI PHY is what we use. That's what we get.
Gen 6 or Gen 5. Or...
Yeah. So that's 7 picojoules per bit. The PCI PHY is Gen 5. I'm reliably told. So, but the CXL only, where you've got a pool in the middle and no local memory, you can see that's 848 watts when you're trying to access any 3 terabytes, 8 terabytes, or 16 terabytes. So it's terrible when you only want to access that 3 terabytes, which was only 49 on a traditional EPIC server. But when you access the really big numbers, obviously we got more bandwidth than local, so it's not bad from that perspective. But you can see that the proposed approach that I'm proposing is still 200 watts less than the CXL pooling only and no local memory.
So I don't want to share this slide. I think this is a little bit different from your previous slide. In terms of
Which slide?
Example, I think you shared, this heat chip slide before, right? On the OCP HPC. It looks like this is.
Yeah, that was an older. So that was when I was preparing the presentation, Michael. So it wasn't quite finished. I've basically shown a number of energy-centric diagrams. So I can't remember at what stage I was at. So, but it was pre-hip chips, that was. So this is more up to date.
So you're gonna share this one, right, with us, right? Is it already?
Yeah, well, I can send Dappy the slides, and we can put this on the audio, and or I can email it to anybody as well.
Okay, thank you.
Oh, actually, it's available on the OCP website. If you go to OCP,
yeah.
I see. Maybe anybody know, just put the link on the chat window, maybe.
Okay.
Thank you.
Can you do that, Dappy?
Yeah, I think so. I don't know if I have it handy. Give me 1 second. But I know DJ keeps sending it out.
Yeah, it's good. It's got them. So you were another question. You were saying between 12 and 14, I think, Dappy.
Yeah. So, here it is. We're out of time, but I was trying to find the.
Well, the slide for just quickly say, slide 14 was my great fight argument. Is we want 2 chiplet standards being bunch of wires on the package, and OIF very short reach for all off package I/O, and all off package I/O is just one thing. It's a memory I/O of short reach, so that every vendor in the world makes their processor or accelerator I/O with this standard, and suddenly
so that part I got. I was trying to find the link, the link between 14 and 11, or 12 and 11. 14
between
or
12 and 11.
No, I'm sorry. From 11 to 14. What is the link from 11 to 14?
Oh well, so obviously, all right, okay. So in 11, where you see the local memory channel is this 1.5 picojoule per bit channel.
Yes.
And that is OIF VSR. It's saying, look, optical CXL shareable local memory using OIF VSR, very short reach. So that's that connection there. And then on slide 14, you see that all of the off-package I/O here is OIF VSR. Is
okay.
That local memory?
You're breaking down what used to be the CPU into components in 14, basically.
In 14, I'm showing that bunch of wires. I'm still showing what you guys are doing with bunch of wires and chip
Yeah,
it. So I'm
okay.
saying if you're on the package, bunch of wires is the way to go. But as soon as you come
Okay.
off package, don't burn 7 picojoules to come off the package, guys, because it's a waste of time.
Although
It's what you want to do is
although there is a universe of people who are extending bunch of wires to the distances you're talking about, which is kind of interesting.
But that becomes a protocol argument then, and I was just focusing on PHYs.
Yeah,
It
that's
was a
fine.
great fight,
But I get
I'm
what
just
you're
talking
saying.
PHY.
Okay, hey Alan, thanks so much. It was pretty interactive.